All right, so we'll continue from where we left off the other time. Now we are on percentage ionization of a weak acid. Right. Now, as it has been explained already, for a weak acid, it only dissociates partially in solution, unlike the strong acid that will dissociate fully. So if you are talking about ionization of a strong acid, it is 100% because all the compound would ionize in the appropriate solvent or in water, right? Good. Now, if we talk about a weak acid, the weak acid will only dissociate partially to produce a few ions. Now, a quantity that will show us the amount of ions dissociated is what we call the percentage ionization. Very simple. All right, good. Now, the formula of finding percentage ionization is concentration of the ionized acid over the initial concentration of acid multiplying 100. So this is for acid, right? Very simple. So the concentration of the ionized acid over the initial concentration of the acid multiplied by 100. Now we have it expressed in the form of HA. If HA is an acid, right? When it reacts with water, we'll have HCO plus A minus ions, right? So the concentration of this one over the initial concentration of the acid multiplied by 100 is what we call the percentage ionization. Now we have an example here. It says that if a 0.2 molar nitrous acid solution contains 9.6 times 10 raised to the power negative 3 molar HCO plus, what's the percentage ionization? So very simple. Now this is the ion, the H plus ions in solution, and this is the initial amount of the acid. So the solution will be the amount of, or the concentration of the acid in terms of the ions all over the initial concentration of the acid multiplied by 100. Very simple. Then you get 4.8. Another question, we have at 25 degrees, a 0.01 molar ammonia solution is 4.1% ionized. Calculate the concentration of the OH minus ions and the NH4 plus. Now I was explaining the importance of 25 degrees. I think I did that in the previous video, that always a equilibrium constant is only a constant at a particular temperature. For which reason, if you are stating the question, we have to state a particular temperature. And so whatever is happening here is happening at 25 degrees Celsius. Once the temperature changes, the constant will also change, right? The equilibrium will shift or the constant will change. So you can just put that in your head. That is why we have to study or state the temperature. Now, the temperature will not be involved in the reaction. Some people are forced to use temperature because it has been given. The fact that we give you temperature doesn't mean you have to use the temperature, right? We are giving temperature because the equilibrium constant is only constant at a particular temperature. Good. Now, the first question is asking us to calculate the amount of OH minus ions and the concentration of NH4 plus ions. So the first thing that will really make our work very easy is when you write the equation for dissociation or ionization of ammonia in water. So ammonia in water will give us ammonium ions plus OH minus ions, right? Good. Now, for us to find the percentage ionization, we need the concentration of each of these because the concentration of them are equal at equilibrium, right? So each of these ones, any of them, so OH minus ions over the initial concentration of the ammonia times 100. Now, this should give us the percentage ionization, right? And so it means we have the concentration of the OH minus ion all over the initial concentration of the ammonia is 0.01 times 100 being equal to 4.1. Now, this is a chemical equation, sorry, a simple linear equation. So I would have 100 OH minus ion concentration is equal to 4.1 times 0.01. Now I'll have the concentration of OH minus ion being equal to 4.1 times 0.01 all over 100, right? Now this will give me 4.1 times 10 raised to the power negative 4. Very simple. So then the question has been solved here. Very simple. That is the solution. Now the second question is asking us to find the concentration of the molar ammonia at equilibrium. Now, if the reaction expression is like this, as I've stated here, initially the ammonia will be the 0.001, then the water is in excess, so we don't really think about it. These ones will be 0 and 0 before the reaction starts. That's initially. Now at equilibrium, we would have X of this one forming and X of this one forming. The water will still be in excess, but then the amount of ammonia left will be 0.01 minus X because it has dissociated to produce these ones, right? 0.01 minus X. And that will be the amount left at equilibrium. And so if they ask us to find the amount left at equilibrium, it will just be the initial amount is 0.01 minus the 4.1 times 10 raised to the power negative 4, right? So that is what has been solved here. A simple subtraction is giving you 0.0096. Then the last question is asking us to find the ionization constant of the ammonia. So the Kb. Now the Kb is equal to the product of the concentration of the product over the concentration of the reactant. So I would have OH minus ions here, the NH4 plus here, all over the concentration of ammonia. So then the Kb will be equal to the concentration of ammonia is this. That is the same. Sorry, and the concentration of the OH minus ion is this one, right? Is the 4.1 times 10 raised to the power negative 4. Now, I forgot to state this, but then if we have the two ionized in solution, the NH4 plus concentration is equal to the OH minus ion concentration. So these are equal, and then that will be the answer we had, the 4.1 times 10 raised to the power negative 4. So that's what I'll have here. I will have 4.1 times 10 raised to the power negative 4, multiplying another 4.1 times 10 raised to the power negative 4, all over the concentration of the ammonia at equilibrium. That will be the 0.0096. And then this one would really give me my answer. So it will give me the 1.7 times 10 raised to the power negative 5 here that way. Very simple. Good. Now, the next question. We are supposed to find the percentage ionization of is 2.5 molar nitrous acid solution. The K of the nitrous acid is 4.6 times 10 raised to the power negative 4. Good. So what can really help us here is that we have to first of all state the formula for percentage ionization. And then percentage ionization is equal to the amount of the H plus ions at equilibrium all over the initial amount of the acid that we are talking about. That's concentration of the acid. Good. Times 100. Good. So this is initial, this at equilibrium. Good. Now it means we have to get the initial amount. The initial amount has been given already, 2.5. Now what we don't know is the amount of the acid at equilibrium. So that's what we have to find. Sorry. Now we can find that by first writing the equation of the dissociation of the acid. So the acid can dissociate partially to give H plus ion plus NO2 minus ions. We can also write this equation as this. Right, good. The next thing we have to know is that the concentration of this one and this one are equal, same for this and this. Now, these two equations are the same, right? This one we consider the H plus, so weighted with water to give us H3O plus. This is just the H plus, the same thing. Good. Now, the Kb expression for this one, the K expression will be the product of the concentration of the product over the product of the concentration of the reactant. We just have one reactant here, so even in the other instance, water is in excess, so we don't really consider it. Good. Now, we can do substitution here. The K is equal to 4.6 times 10 raised to the power negative 4 is equal to all, this one can be said to be x squared. Assuming the dissociation of this is x and then this is also x, right? Then I'll have x times x, giving me the x squared here. Very simple. Good. Then the nitrous acid is 2.5. So I can make x the subject, x being the subject. Okay, let me make it slowly. X squared will be equal to 4.6 times 10 raised to the power negative 4 multiplying 2.5, right? Good. Then x will be equal to the square root of 4.6 times 10 raised to the power -4 multiplying 2.5. Good. So then I'll get the value of x as has been illustrated here. So the x will be the 0.034. Good. Now, right after that, what we can do is that we can find our percentage by incorporating the values you have gotten into this formula. So therefore, percentage ionization will be equal to the acid. The acid is 0.034 all over 2.5 multiplying 100, right? Good. And this will give me my final answer, the 1.4. Now, this process is quite long. We can use a shorter one. This will be the shorter method. This should be our shorter method. So instead of okay, so let me clean the surface here and then good. So the same question. Now the first one was for me to oh no, that's not this question. So let me just clean this part. The first one was for me to find the concentration of the H plus ions. Now for a weak acid, you have a simple formula that we can use to find the concentration of what? Of the H plus ions. A very simple formula. Good. So the formula is that the concentration of the H plus ions is equal to the square root of KAC. Good. So the H plus ion concentration will be equal to square root of Ka. The Ka is 4.6 times 10 raised to the power -4. The C is 2.5 times 2.5. C is concentration. Good. Then this can give me my answer, right? And then right after getting your H plus concentration, which is the 0.034, we can just incorporate that into this one. Percentage ionization is equal to 0.034 over 2.5 times 100. Very simple. Good. Now, more exercise. So then they ask him what's the percentage ionization of acetic acid in 1 molar, 0.1 molar, 0.001 molar. The acetic acid. Then they have given us the key. Good. So what can make our life very easy, apart from the normal one shown in the slide, is that we use this formula. The H plus concentration in each case will be square root of KAC. The K has been given, the C has also been given. So for the first concentration, the 1 molar, the H plus concentration would be square root of the K, that's 1.8 times 10 raised to the power -5 times 1. So that would be 2.828 times 10 raised to the power -3. Then, if I want to find my percentage, it will be this one over the initial times 100. So it will be 2.828 times 10 raised to the power -3 all over 1 times 100, right? And this should give me 0.2828%. Very simple, right? 0.2828%. Very simple. Good. Now, if I'm talking about the 0.1 molar, my H plus ion concentration will be equal to square root of KAC. That is 1.8 times 10 raised to the power -5 times 0.1. Oh no, I didn't punch my first value well. It would interrupt my answer. Instead of 1.8, I punched. Sorry, so this one is giving me the value here is supposed to be 4.2426 times 0 to the power -3. So my percentage should be, okay, let me cancel this. So it will be 4.2426 times 10 raised to the power negative 3 all over 1 times 100, right? And that should be 0.424%. Very simple. Then this one, the H plus ion concentration here will be 1.342 times 10 raised to the power negative 3, right? Good. So the percentage will be 1.342 times 10 raised to the power negative 3 all over 0.1, all over 0.1 times 100, right? Good. So then I'll have 1.3. I'll have, let me write it here, 1.342%. Very simple. Now, if the concentration is 0.01, then the H plus concentration is still square root of KAC. That is square root of 1.8 times 10 raised to the power negative 5 times 0.01. So 1.8 times 10 raised to the power negative 7. So I'm typing 1.8 times 10 raised to the power negative 5 times 0.01. And that is giving me H plus concentration to be 4.243 times 10 raised to the power negative 4, right? Good. Now the percentage ionization will be the 4.243 times 10 raised to the power negative 4 all over 0.01 times 100, right? So this one will give me 4.243%. Good. So realize that we've been able to calculate our percentages simply by using this formula. Now, one thing you observe is that the concentration here is decreasing. Now, decreasing concentration can also mean increasing dilution, right? So if you decrease your concentration, it means you are diluting the solution more, right? Now, what is happening to the percentages? The first percentage we had was 0.4, then we came to 1.3, and then we came to 4.2. Now, you realize that as the concentration is becoming small, the percentage ionization is increasing, right? That is to say that upon dilution, there are more ions dissociated into solution. So that is the general fact that we want to deduce from this, that when you dilute a solution more, that is for a weak acid, you make it dissociate more to produce more ions in solution, right? That is it. Very simple. Very simple. So the question has been solved here. Very simple. Good. So then they said that for a weak acid or base, percentage ionization increases with increasing dilution. Now, another question for us to digest. So this question is talking about a polyprotic acid. We've already mentioned that for a polyprotic acid, the H plus ion is donated in steps, right? So the first H plus will come, the second one will come, the third one will come in that manner, right? Good. So we have 3.0 molar F3PO4 solution. Then we are supposed to first of all calculate the concentration of the H3O plus ions. So we'll focus on that. Now the first thing I have to do is I have to write the dissociation constant. Sorry, an equation showing the dissociation of this one, of the H3PO4. So I have H3O plus H2PO4 minus, right? Good. Then initially, this one will be 3.0. This is in excess. This will be 0, and this will be 0. At equilibrium, this will be x, and I'll have x of this formed, and this will be 3 minus x. 3 minus x. Very simple, right? Good. Then we have our KA1 expression. Now it's KA1 because in the first step, it is just given one of the hydrogens. Even though it's capable of giving 3 hydrogens, each of them will be given in a single step, right? So the KA1 will be equal to the concentration of the H3O plus multiplying the concentration of the H2PO4 minus all over the H3PO4. Good. So the KA1 will be 7.1 times 10 raised to the power negative 3, as the question has stated here, is equal to, now this is x times x, that will give me x squared all over this one. That is the acid itself, 3.03. Then I'll have the x squared being equal to 7.1 times 10 raised to the power negative 3 times 3. Good. Then I will have x being equal to the square root of 7.1 times 10 raised to the power negative 3 multiplying 3. Good. So x should be equal to I'll have my x being equal to 0.146. Very simple, 146. Now that will be the concentration of the H3O plus. That will be the concentration of the H3O plus. Very simple. Now the B says I should find the concentration of the H2PO4 minus. Now you realize that from this equation, the H3O plus is X. This one is also X. So we are saying that H3O plus concentration is the same as the H2PO4 concentration, which is 0.146. So we have solved the second one too. That is just the 146 molar. Then the next one is HPO42 minus. So then how do we go about that one? So H2PO4 minus will also dissociate to plus water, and then it will give me the H3O plus constant plus the HPO42 minus. That's this one, right? Good. Now, what's the concentration of the H2PO4? That is 0.146. Then initially, this one will be in excess. This will be this one. We already have H3O plus in solution. It's also 0.146. Then this is 0. This is 0. We have not formed this in solution, so it's 0. Good. Then at the next step, we would have some dissociating. So assuming Y has dissociated, then I would have 0.146 minus Y here, right? The water will still be in excess, so we don't consider it. Then this one will be 0.146 plus Y, and then this one will be Y. Now, why are we adding the Y? Here is coming from the acid. The acid here is dissociating to give me the Y, right? But we already have H3O plus, so this will just add to this. And then the Y here will also be here. Good, very simple. Now the Ka2 expression will be the concentration of the product, H3O plus, then HPO42 minus, all over the H2PO4 minus. Good. So this is it, right? Then we have the value for this one. So 6.3 times 10 raised to the power negative 8 is equal to the acid. What is the concentration of the acid? 0.146 plus Y. That's at equilibrium. Then the H3PO4 is just Y. All over that of the acid initially. So that's 0.146. Now at this point, we make some assumption. The assumption is that the value of Y that we are about to find, because a weak acid dissociate partially and give you just few ions in solution, right? And so if we compare, if we add the 0.146 plus Y, approximately is equal to the 0.146 because the Y is a very small number, right? So we assume that the whole of this That's 0.146 plus y is approximately equal to 0.146. That's what we do because it's very small. So then I would have 6.3 times 10 raised to the power -8 is equal to 0.146 y. This one multiplying y all over 0.146. So this one will cancel this one out, right? Then I'll have y is equal to 6.3 times 10 raised to the power -8. So you realize that will be the concentration of the HPO4 2 minus. HPO4 2 minus, right? Good. The next question is asking us to find the concentration of the PO4 3 minus. So let me clean this part and use it. But then we'll follow the same sequence. So follow the same thing as we've done already. Right. All right. So good. Now the last question. So we take it from this one, HPO4 2 minus plus water. So that will give me the H3 plus PO4 3 minus. Good. Now, when we get here, the HPO4 2 minus plus water, we've already found the concentration of the HPO4. So initially, it would be 6.3 times 10 raised to the power -8. Water is in excess. Now the acid, we already have acid in the medium, right? It was approximately equal to the 0.146. So we still maintain that. Then we make this one M, assuming it's M, right? Sorry, initially it will be 0. It will be 0. Now, assuming this one was able to dissociate by a quantity M, so then the amount of this at equilibrium will be 6.3 times 10 raised to the power -8 minus M. The water will still be in excess. This will be 0.146 plus M, and this will just be M, right? Good. Now, I have made a mistake with this calculation. It's not really major because this one too, you had to consider 0.146 minus Y, right? Minus the Y, because at equilibrium, it was 0.146 minus Y, right? Good. But then again, the argument we are putting across is that the minus Y will not really cause a lot of change because the Y is a very small number. So then we assume that 0.146 minus Y is approximately equal to 0.146, right? So it wouldn't really cause a lot of change down here. Very simple. Very simple. Good. All right. So the formula for finding the Ke. So we have the Ke3. This is the third dissociation, right? Ke3 is equal to the product of the concentration of the products over the product of the concentration of the reactant. So this is PO3 minus the reactant here is the HPO4 2 minus. Good. Then we substitute, or we have to substitute. Good. So we'll have the Ke3 4.2 times 10 raised to the power -13. Oh, my 13 is 2. Okay, -13 is equal to, now the acid here is 0.146 plus M, right? The sulfate ion here is M, and then the hydrogen sulfate here is 6.3 times 10 raised to the power -8 minus m. Good. Now, usually what we see with regards to the addition and subtraction is that the m that we are about finding is very small. Because it's very small, if you add it to this number, it will just be negligible. So we can just neglect this plus m here. In the same vein, we can also neglect this minus m here, right? So this will be what we'll have. Then if I do my change of subject here quickly, m will be equal to 4.2 times 10 raised to the power -13. -13 multiplying 6.3 times 10 raised to the power -8 all over 0.146. Now, if we do this very well, we should be able to arrive at the final answer, the final concentration. Now, the question has been solved, so we can just refer. This will be our final answer. The 1.9 times 10 raised to the power -19, and that should be the concentration of the PO4 3 minus. Very simple. Good. The next question. Given two bottles, each of which contains 0.1 molar solution of unidentified acid. One bottle is labeled K is equal to 7.2 times 10 raised to the power -4, and the other is labeled K 1.9 times 10 raised to the power -5. Which bottle contains more acidic solution, and which bottle has the acid with larger pK? Good. Now, we have given us two bottles, the same concentration. They are weak acids, unidentified ones, and then you have been given the K. So which of them is more acidic? Now, K is directly proportional to acidity. That is, the higher the Ka, the higher the acidity, right? The higher the K, the higher the acidity. K gives us an extent of how the acid will break down to keep H plus ions. And so we realize that between these two numbers, 7.2 times 10 raised to the power -4 is bigger. Now, because that is the bigger number, the bottle that is calibrated K equal to 7.2 times 10 raised to the power -4 is the stronger or is the more acidic solution. Very simple. Now, you realize that the relationship between K and pK is inversely proportional. So, like, if the K is high, the pK is low, right? Good. So the one that will have a larger pK will be the one that will have the lowest Ka, and that will be the bottle calibrated 1.9 times 10 raised to the power -5. Good. Now, there's another question. Vinegar contains acetic acid and is used in salad dressing. What if acetic acid was a strong acid instead of a weak acid? Would it be safe to use vinegar as salad dressing? Now, we are asking that vinegar contains acetic acid, right? Good. Now, acetic acid, we all know, is a weak acid. And then the question is that if it were to be a strong acid, would it have been safe? And then the answer is no, it wouldn't be safe, because when we learn the properties of acid, we said acids are corrosive. They can burn tissue. They can actually burn living tissues. I don't know if you have seen some before, but then acid can actually burn living tissues upon exposure. So there's no way we use any strong acid because of their corrosive action. There's no way you can use any strong acid as a food for us to consume. And no, we'll not use any acid which is strong, right? The weak acid, because they don't really have a lot of corrosive activity we can use, but not the strong acids. Very simple. Good. Now, the next question. Consider the given acid ionization constant. Identify the strongest acid. So we have talked about Ke already. Now, the question here is different because we want the strongest conjugate base. The strongest conjugate base. Now, which one will be the strongest conjugate base? There's a relation between the acid strength and the conjugate base strength. The acid strength, that's if you have a very strong acid, right? A very strong acid, sorry, the conjugate base will be very weak, right? Now, if you have a weak acid, its conjugate base will be very strong. If you have a strong acid, its conjugate base will be very weak. So it's like the strength of the acid is inversely proportional to that of the conjugate base. And so what we have to do here is that we have to identify the acid which is the strongest. Now, if we see the acid which is the strongest, its conjugate base will be the weakest. If you are able to identify the acid which is the weakest here, its conjugate base will be the strongest. So if we want to find the weakest here, the K is directly proportional to acidity, right? Directly proportional to acidity. So we want to find the weakest acid, right? And it's the one that has the lowest K value. Now that will be 4.9 times 10 raised to the power negative 10, right? This will be the weakest acid. Now the weakest acid here will have the strongest conjugate base. Will have the strongest conjugate base, right? Good. So if this is the weakest acid, now the HCN, hydrogen cyanide, will dissociate partially and give me H plus ions plus Cn minus ions. This will be the conjugate base, and this is the strongest conjugate base available. So the answer here is D. Very simple. O2 ionization of water. O2 ionization of water. Now, the idea, I think the topic here is self-explanatory. We are talking about O2. O2 means self, right? Ionization means you are producing ions. And so we are saying that water on its own can automatically or by itself can produce ions. That is what we call O2 ionization of water. So water producing ions, right? Good. Now we are saying that water can produce equal amount of HVO plus ions and OH minus ions, even in the pure state, right? And that's what we call autoionization. Now, there's a chemical equation showing that. So one water molecule will act as an acid, and then another one will act as a base. So the one that acts as acid will donate a proton, to the base. And so we'll have HVO plus here, and then this will be the conjugate acid. After accepting the proton, this will be the conjugate acid. And then after donating the proton, this will be the conjugate base. So the base written here becomes the conjugate pair that we are talking about. Good. Or we can condense it and say 2 moles of the water will dissociate and then form HU plus, that's hydrozonium ion and the hydroxide ion in solution. Good. Now we can write equilibrium constant for the ionization of water, and then that will give us this one. Good. Good. Now, we are saying that the Kc here is equal to Kw. I think we've done calculations on Kw already, right? So what we say is that the water here is in excess and is very large. So then we can just multiply the water concentration by the Kc here, and then we'll just have the Kw, which is equal to the concentration of the H2O plus ions, multiplying the concentration of the OH minus ions. Very simple, right? Very simple. Cool. So this is what we call the Kw, and the Kw is known as the ionic product of water, or ionization constant or dissociation constant of water, right? Now, per calculation, we know that the Kw of water is 1 times 10 raised to the power negative 14. Because the concentration of the acid and the base are equal, let me write it. The acid is equal to the concentration of the base, and that is equal to, okay, this is negative 14. That's equal to 1 times 10 raised to the power negative 7. So each of them is negative 7. Now, during your calculations, we don't really consider, let's say if something dissolves in water, we don't consider the ionization of water, the contribution coming from water. But then if it happens that the concentration of the acid we are talking about is very low, then we consider the contribution of the H plus coming from water. What I'm saying is that on a normal day, because of this concept, we know that water can also produce H plus ions and OH minus ions in solution. When we are dealing with strong acid, strong bases, when we are dealing with highly concentrated weak acid or weak base, right? We don't consider the contribution from the water in terms of the HCO plus and the OH minus ions. But then if you are dealing with very dilute solutions, then we have to consider the H plus coming from water or the OH minus coming from what? Coming from water. And then the value for the H plus coming from water is 10 raised to the power negative 7. Same for the OH minus coming from water. Very simple, right? Good. So we are saying that because water is a pure liquid, its concentration does not appear in the equilibrium constant. Now, the equilibrium constant expression becomes Kw is this. Experimentally, we've realized that 25 degrees Celsius, the concentration of OH minus is same as the concentration of the H plus ions, and that is 1 times 10 raised to the power -7 molar. Good. So this is it. Then that will help us know that the ionization product of water is 1 times 10 raised to the power -14. Now we are saying that the value is very small. 1 times 10 raised to the power -14 is 0.0001. Very long value, right? Very small. Now it confirms that only a small proportion of water can ionize or can produce ions or can be converted to ions, right? Because the value is very small, it shows that just a small proportion of what water is converted to the ions, right? Good. That is concentration of ions due to the auto ionization is very small. That's what we are saying, very simple. Then we are saying that the very small volume of Kw means that auto ionization of water does not contribute significantly to the H plus ions of most acid or to the OH minus ions of most bases. Very simple. Now we are saying that we can ignore the contribution of the auto ionization in most calculations of acid and bases. However, if the acids or bases are extremely weak, or if the concentrations are extremely low, then we have to consider the dissociation of the water. That's what we are saying by the last point. Now we are saying once again that the Kw is equal to 1.00 times 10 raised to the power -14. Now we are saying that in any aqueous sample, right, as the value of one increases, the value of the other decreases. So if the value of the H plus is increasing, then the value of the OH minus is decreasing. But always it happens that their product is 10 raised to the power -14. That is their product, right? So assuming we have 10 raised to the power -7, 10 raised to the power -7, right? On a normal day. Now, if the acid increases to 10 raised to the power -6, the base becomes 10 raised to the power -8. If the acid goes to 10 raised to the power -5, the base goes 10 raised to the power -9. So as this one is increasing, then the concentration of this one will decrease. But always it happens such that if you multiply, then the product will be 1.0 times 10 raised to the power -14. Now we are saying that in any solution, if the concentration of the H plus is bigger than the OH minus, then we have an acidic solution. If the H plus is less than the OH minus concentration, we have a basic solution. And then if the H plus and the OH minus concentration are equal, then we have a neutral solution. Good. Relationship between K and KB. Yes, I think the most important thing, we have a way of proving which you might never be asked how to prove it. But then the most important thing you have to know at this point, two things. The first one is that the K multiplied by the KB will give me the KW. So Ka multiplied by KB will give me the KW, right? Good. Now we can find the log of it to show that the pKa plus the pKb is equal to the pKw. Now we can also see, so we are not done. We can see that the pKa plus the pKb is equal to 14. So these are the two most important equations that you have to know from the slide, right? Very simple. That the K times the Kb is equal to Kw, and then the pK plus the pKb is equal to 14. Very simple. Good. Now pH and pOH definition. So what is pH? Now pH is the measure of how strong or weak an acid is, and is defined as a negative logarithm of the hydrogen ion concentration or negative logarithm of hydrozonium ion concentration to the base 10. Now, if we talk about pOH, it's a negative log of the OH minus ions in solution. Now, what will help your life to be very easy with regards to this chemistry, that you have to always remember that P, you might meet P in so many instances, but then P here is negative log. So whenever you see P, there's negative log to the base 10. So then if I say pH, you know it's negative log of the H plus ion concentration. If I say pOH, it means it's the negative log of the OH minus ion concentration. Very simple. Very simple. Good. So a question here, we give you the H plus concentration. You just find a negative log of it and then you get your pH. Now there's a note here we have to take note of. In real solutions, not concentrations, but ion activity should be used for calculation, especially the pH definition uses not minus logarithm or concentration, but minus logarithm of activity. Now, what happens? This is a whole concept that we have to learn, or we'll learn as we go along. But then in real solutions, what we have been talking about so far has been focused on ideal solutions. Then in ideal solutions, what happens is that if I have HCl, right? HCl can dissociate fully to give me H plus ions plus Cl minus ions. So if I have 0.1 of the HCl, I'm saying that I have 0.1 of the acid in the medium, the H plus ions in the medium. That is in the ideal case. In the ideal case. Now, if you talk about real solution, even after the complete dissociation of these ions, because it's negatively charged and it's positively charged, the ions still interact. And so the ions or the compound is ionized but has not been separated. So you realize that some of these molecules are still surrounded by the oppositely charged particles. And so it is only some small portion which is free, or there's a portion of it which is not free. And then the portion of it which is not free will not contribute to the acidity, right? Good. And so this is the concentration, all right, but then this is not the activity. If we talk about the activity, we are talking about the actual ions which are mobile in the solution and can contribute to the property of the solution. That is what we mean by activity, right? And so when we are talking about ideal solutions, we focus on the concentration of the solutions. But if we come to real solutions, real is just the normal real that you know, real life. Real solution, we talk about activity because we know there's something called ionic interaction. And then if ionic interaction is not one, the concentration is not equal to the activity. And so in any instance, if I give you the activity and I give you the concentration, use the activity because the activity is the true reflection of the actual ions in the medium, right? Of the actual ion, of the mobile and the free ions in the medium. The concentration is just a theoretical way. That is the ideal and the ideal circumstance, which does not really happen. Good. So that's the note. Now, there's a picture, very simple, showing us that if the pH is equal to 1, then we have a very strong acid. Actually, on the pH scale, the strongest acid we can measure will be 1 because it ranges from 1 to 14, right? And then as you move to your right, the acid will decrease. So you see the H plus diminishing and then the OH becoming more prominent. So you get to 14, and then 14 will be complete basicity or alkalinity, right? When you get to 7, 7 is neutral. Good. Closer to the 7, the borders of 7, we have weak acid and weak base. Weak acid to the left, weak base to the right. Very simple. Good. Now, we are saying that note that in any solution, as the H plus concentration increases, the OH minus decreases. Very simple, right? So now the table here shows the same thing, that the concentration of the H plus here is decreasing, right? Now, once it's decreasing, the pH will be increasing. Good. Now, if we come here, the concentration of the OH minus ions, as this one is decreasing, is also increasing. It's also increasing. And the pH the pOH will also be dropping. The pOH should be dropping. So it makes sense. When this one is decreasing, the value of the OH minus is increasing, right? And then the pH is increasing, the pOH is decreasing. Very simple. Good. Now, let's talk about more features of the pH scale. So they are saying that a change of a unit corresponds to 10 folds. Now, because we are dealing in logarithm, this one, it becomes very easy if your math is very good, right? Because we are dealing in logarithm, you know log of 10 is log of 10 is 1, right? Log of 0 is 1. Log of 0 is 1. Log of 10 is, let me get my math well. Log 10, that's 10 raised to the power 1. Good. Log of 10 is 1, right? Log of 10 is 1. I'm confirming my math before I continue. Good. Log of 10 is 1. Good. So if you see 1 on the pH scale, let's see, we have 2 10s, right? And then one of the pH is 2, the other one is 3. Now, the difference between 2 and 3 is 1. That's 3 minus 2 is 1. But then we are not talking about 1. The 1 here is in terms of log. If you talk about the normal numbers, it is 10. It is 10, right? We are talking about 10 in that case. It means if I have an acid which has a pH of 2 and another one which has a pH of 3, ideally, you know, the 2 will be stronger than the 3, right? Good. And then it's stronger than it by 1 unit. That 1 unit means 10. And so it means that this acid, assuming the 2 is A and then the 3 is B, the A is 10 times stronger than the B. Are we following? The A is 10 times stronger than the B. If we have a such that one is 2 and then the other one is 4. So A is 2, B is 4. Now I realize that the difference here is 2, right? The 2 is 10 raised to the power 2. That is 100. And so what it actually means here is that the A is stronger than the B in terms of the acidity by 100 times, not 2 times. And so a unit, we are saying that a unit on the pH scale corresponds to 10 folds. Correspond to 10 folds, right? An example can be cited over and over again in so many other instances. The same example can be cited in so many other instances. The same example can be cited. We'll find more examples around. These are some materials on the market, and then these are their respective pHs. We can take note of them. Good. Now, there's a question here. We are supposed to match pH values to their correct description. Now I have 13.77, 10.3, 7, 4.3, and 0.2. 0.2 is the smallest number here. That should be the most acidic here. So we give it strongly acidic. Now 13.77 is the biggest number here. So that should be the strongest base, right? So we make it strongly basic. 7 is neutral. So 7 is neutral. Then 4.3 is acidic. So I give it a weak acidic here. 10.3 is basic. So I give it weakly basic here. Very simple. The next one is that if the pH of a solution is 3.4, what is the hydrozonium ion? What is the hydronium ion concentration? So hydrozonium ion concentration, that's the H3O plus, right? Now you know pH is equal to negative log of the H3O plus concentration. So 3.4 is equal to negative log of the H3O plus, that's the hydrozonium ion concentration. Then I'll divide it by negative 1, negative 1. So negative cancels negative. I'll get log of the H3O plus is equal to negative 3.4. Then I'll have the log inverse or the anti-log. So I have H3O plus being equal to 10 raised to the power negative 3.4. And that would be equal to, I think the answer is in here. So that this is the answer. 3.98 times 10 raised to the power negative 4 molar. Next question. Suppose solution A has a pH of 6.0, B has a pH of 7.0, right? Which of the following statements is correct? Now, they want to compare the acidity. Generally, you should know that if A is 6.0 and B is 7.0, A is more acidic than B. Very simple, because the smaller the number, the higher the acidity, right, on the pH scale. Good. So, and I told you, the difference between the 6 and the 7 is just 1, right? And 1 unit on the pH scale corresponds to 10 folds. What we are saying is that the A is 10 times stronger than the B, right? The A is 10 times more acidic than the B. So it's just option A. The answer is option A. The solution A is 10 times more acidic than solution B. Good. The same type of question. Now, we are saying that stomach acid is approximately 2, sour milk is 6. So then you should know that the 2 is more acidic than the 6, right? In the same way, we can say that the 6 is more basic than the 2. But then the answers are in terms of acidity. So let's stick to that. So the 2 is more acidic. How acidic is it? Cool. So the difference between 6 and 2 is 4. Now the 4 here is 10 raised to the power 4. That is 10,000. Right? 10,000. Cool. So what we are saying is here is that the stomach acid is 10,000 times more acidic than the sour milk. Very simple. Good. Now, the next question. A student accidentally splashes a concentrated strong acid onto the bare skin. Now you've splashed conc acid onto your skin. We are seeing which of the following is the most effective and safest course of action. Dry it. No, you don't dry it. Flash the area with water and dilute weak alkaline. Sorry, dilute weak acid. No, you don't add weak acid if you have been burnt by acid. Then you flash the area with dilute any OH then water. Any OH is a strong base. That wouldn't be advisable to put a strong base on an area which has been affected by a strong acid, knowing very well that the neutralization reaction is an exothermic reaction that will produce heat, which can actually cause burn again. So nobody will advise you that put a strong base on your skin if you have been attacked by a strong acid. No, it would hurt you more. Next one, flush the area with water and then dilute solution of. This one makes a little sense because you have to wash the place with water. Once you are splashing the place or washing the place with water, we dilute the content there. And then the bicarbonate ion here, sodium bicarbonate, is a weak base. So the weak base will not really cause a lot of harm in you, right? Very simple, very simple. So this thing makes a lot of sense, actually. This thing makes a lot of sense, right? The last one doesn't make sense, so just G it. Good. So we've said that you can read through this one. The next question. The solution A with pH of this. Okay, so they are comparing and they are saying they are asking, is a solution with a pH of 9.58 more or less acidic than solution B, in which the H plus concentration is 4.3 times 10⁻⁻10 molar. Good. Now, what can help us to compare whether it's more or less acidic is that you have to find the pH of the second one too, right? Find the pH of the second one. But this one, if you have learned your chemistry very well, you don't have to worry your head because it's clear. But let's find it. So the pH of the second one will be pH is equal to negative log of H plus ion concentration. Now pH is equal to negative log of the 4.3 times 10⁻⁻10. So negative log of 4.3 times 10⁻⁻10. So we get 9.37. Good. So then one is 9.5, the other is 9.3. The smaller number is the more acidic one, right? Good. So they are asking if this is more or less acidic. So then we can see that this is less acidic than this one. It is less acidic because it has a bigger number than it. Very simple. Very simple. Good. So calculate the H plus, okay, concentration for a solution with pH of this. So we've done this one before. The pH is equal to negative log of the H plus ion concentration or H3O plus ion concentration. I'll be using these terms interchangeably because they imply the same thing. Negative log of H plus concentration. Then divide by negative, you get negative 4.08 is equal to log of H plus concentration. And then the H3O plus concentration will finally be equal to 10⁻⁻negative 4.80. And that should give you a final answer. Good. Now, we are saying that at this point, the most important thing that you have to know is that the pH plus pOH is equal to 14. Very simple. Such that if I have pH, if I make pH the subject here, I'll get pH equal to 40 minus pOH. So sometimes you get your pOH. What do you do to get your pH? You subtract the pOH from 14 to get your pH. Very simple. Good. So you are supposed to calculate the pH of the following, right? And indicate whether they are acidic or basic. So the first one, we have been given the H3O plus solution. H3O plus. So then we have pH is equal to negative log of the H3O plus concentration, square bracket, pH is equal to negative log of 1.8 times 10⁻⁻4 molar. Now, that should give me the 3.74, which is acidic. Anything less than 7 is acidic, right? Good. Then the pH, because we have the ions in OH minus concentration, we have to first of all find the pOH. The pOH is negative log of the OH minus ion concentration. Then the pOH will be equal to negative log of the 1.3 times 10 raised to the power negative 2. Good. Now you find it. Let me punch it to negative log of 1.3 times 10 raised to the power. So then I'm getting POH is equal to 1.89. Good. Then I have to find my P. So P is equal to 14 minus 1.89. Now pH is equal to 12.11. 12.11. Very simple. Right. Very simple. Good. So that's it. And once it's 12 is basic. Anything more than 7 is basic. Very simple. Good. Now the concentration of the H plus in a solution is found to be this. Find the OH minus ion concentration. So if you remember very well, I said that the KW is equal to concentration of the H plus ion and then the OH minus ion, right? That's KW. Good. Now, the KW, we know the value as 1 times 10 raised to the power negative 14, right? Good. If I consider just this and make the OH minus the subject, it means I'll divide the side by H plus ions. Divide the side by H plus ions. This one cancels this. It means the OH minus ion concentration is equal to KW all over H plus. And then what's the KW? The KW is 1 times 10 raised to the power negative 14 all over 3.5 times 10 raised to the power negative 5. So you punch this and then you get your answer. Very simple. Next question. A research chemist adds this amount of mils to a gas to pure water at 25 degrees and obtain a solution of this. Calculate the OH minus. So it's the same thing. You just use what we did here. That's the OH minus concentration is equal to KW all over the H plus concentration, right? Good. And then that should give you an answer. Very simple. And then once you realize that the question said we should find whether it's acidic, basic, or neutral. Once you realize that the H2O plus ion is greater than the OH minus ions, then it is acidic, right? Good. Next one, calculate the pH of this one. We have given you the acetic acid solution. Concentration, yes. So the simplest way is to use your formula. The H plus ion is equal to square root of KE times C. So the H plus ion concentration should be equal to square root of the Ke is 1.74 times 10 raised to the power negative 5 times the C. The C is 0.005, right? This one can help us to get our H plus ion concentration. Right after getting our H plus ion concentration, we can use that to find our pH. pH is negative log of. So this will be the H plus concentration that we will get after this. You can decide not to go through all these steps, but use this formula. It will just give you an answer. And then the pH will just be negative log of this one. That will give you the 3.53. Very simple. Very simple. Okay. Okay. All right. So a new question. Dimethylamine. Dimethylamine is a key intermediate in detergent manufacture and has a Kb of 5.9 times 10 to the power negative 4. What is the pH of 1.5 molar dimethylamine? So you're supposed to find the pH. We have been given the Kb and then the concentration. Now the pOH or the OH minus concentration will be equal to square root of Kb times C. So you can use this, very simple. Then OH minus concentration should be equal to the square root of, as a Kb. Kb is 5.9 times 10 raised to the power negative 4, multiplying the C, that is 1.5. Good. Now, these formulas, before you use them, please ask your teacher whether it's appropriate to use them, because these are simple ways, and then she might really be expecting you to do different. Good. So then you point to this in your calculator. So you are getting 0.0297 molar. Then you can find your POH, which is the negative log of the OH minus ion concentration. Then POH should be equal to negative log of 0.0297. And then the POH is equal to 1.53. pH should be equal to 40 minus POH. And then pH will be equal to 40 minus 1.53. I'm getting 12.47. That's pH equal to 12.47. Very simple. Good. Next question. Consider two aqueous solutions of different weak acid, HA and HB. What if all you know about the two acids is that the Ka value of HA is greater than that of HB? Can you tell which of the acid is stronger than the other? Can you tell which of the solution has a lower pH? Defend your answer. So we have been given two solutions, HA and HB. The first thing they have told us about the solution is that HA has a greater Ka value than HB. Now, you know, the higher the Ka value, the higher the acidity, right? Good. And so the HA that has a greater Ka value will have a higher acidity than the HB. Very simple, right? Good. So we can tell. Good. And then the one that has a lower pH. Now, the lower the pH, the higher the acidity, right? The pH is inversely proportional to acidity. So the lower the pH value, the higher the acidity. So we are saying that HA is more acidic, right? Because it's more acidic, then it will have a lower pH. Because it's more acidic, then it will have a lower pH. More acidic, it will have a lower pH. Very simple. Next question. Calculate the pH of 0.1 molar aqueous hypochlorous acid. Now, the H plus concentration is equal to square root of KAC. So H plus concentration is equal to square root of 3.5 times 10 raised upon negative 8 times the C, which is 0.1. Then you point this in your calculator, you get the answer. Then you find the pH is equal to negative log of OH minus ion concentration. That should give you the final answer, the final pH. Good. Now, acid and base properties of salt. Acid and base properties of salt. So a salt is formed by the neutralization reaction between an acid and a base. Very simple, right? Now we are saying that dilute aqueous solutions of salt comes in 4 types. Those derived from strong acid, strong base. Those derived from weak acid, strong bases. Those derived from strong acid, weak bases. Back to business. All right, so those derived from weak acid and strong bases. We have others derived from strong acid, weak bases. Then we have weak acid, weak bases. Now, all these salts would display different properties in solution. They will display different properties. If you have a salt from a strong acid, strong base, you form a salt. That salt do not undergo hydrolysis. And so the salt is virtually a neutral salt. We'll talk about all those in the subsequent slides. If you have salt from a weak acid, strong base, the salt is basic, right? If it's from a weak base, strong acid, the salt is acidic. If it's from a weak acid, weak base, it depends on the Ka and the Kb of the acid and bases, right? Good. So we'll talk about all these as we go along. So this is an example of a salt formed from a strong acid, strong base. This is a strong acid, this is the strong base. We form a salt and water. This salt is a neutral salt, sodium chloride, neutral salt. Now we are saying that when sodium chloride is placed in water, the resulting solution is neutral, that's pH equal to 7, right? But then if you pick another salt like sodium acetate and you put it in water, you get a basic solution. Why? Now the whole reason is hydrolysis. Hydrolysis. Now hydrolysis is just talking about how the ions of a salt will interact with water. How the ions of a salt will interact with water. Good. So we are saying that when an ionic salt dissolves in water, both the free cations and anions are formed, right? So if you have something like NaCl in water, we form Na plus ions and then Cl minus ions. So we have free cations and free anions being formed, right? Now we are saying that the salt will contain both cation from the base and anion from the acid. So if you consider it very well, this cation is from the base. What base? NaOH, right? And then the anion, the Cl minus here, is from the acid HCl, and that is what always happens in the salt. The cation is from the base, the anion is from the acid. That is what we are saying here. Now we are saying that we need to examine both ions in order to determine the acid-base characteristic of or character of a salt. Typically, this is a three-step process. We write the reaction that dissociates the salt into its constituents. Then we check for the cation hydrolysis. We check for the anion hydrolysis. Good. Now, there are some things that we have to pay attention to, and these ones will guide us through the discussion of this subtopic. So we are saying that the conjugate base of any strong acid is weak, so it would not undergo any significant hydrolysis. Now, I've already said this before in one of the questions we solved, that if you have a strong acid, its conjugate base is very weak. If you have a strong base, its conjugate acid is very weak. And then if you have a weak acid, its conjugate base is very strong. If you have a weak base, its conjugate base, if you have a weak base, its conjugate acid is actually also strong. Do you get it? So that's the idea we are communicating here. That's now the conjugate base of every every strong acid, sorry, is weak. Because it's weak, it will not undergo hydrolysis. But then in the same way, the conjugate acid of a strong base, right, is also weak and then will not undergo hydrolysis. Ions that do not undergo any significant hydrolysis will have no effect upon the pH of a solution and then leave a neutral solution. The reason why NaCl will have a neutral, will produce a neutral solution is that the Na here is from the base, NaOH, which is strong. Because it is strong, the conjugate acid here is weak. The Cl is from HCl, which is also strong, right? Now the Cl here, because it's from the strong acid, is also weak. Are we following? It's also weak. Good. So then because these two are weak, they will not undergo hydrolysis, that they will not interact significantly with water, and then they will make the solution neutral. That's the pH of 7. Let's move on. So salts that do not have ions that do not hydrolyze. So we have to take note of all these ions. When these ions are in the salt, they will not cause hydrolysis. That's they will neither produce acidic or basic pHs. Now, these are bases or anions that do not hydrolyze. Sorry, anions, not bases. Anions that do not cause hydrolysis in water. So they only produce acidic or basic solutions. These are them. We have to take note of them. Good. Good. Now, all group 1 metals, lithium and calcium, and all metals with cationic charge of +1 are neutral. Good. Salt containing a combination of only these cations and anions are neutral. So we are saying that if you have any salt that has any of this cation or anion, if you have both of them paired, then it becomes neutral, right? If you have any cation or anion outside the ones listed here, then we are getting either acidic or basic solution, not neutral solution. We are saying that salt that contain highly charged metal cations, Fe3+, produce acidic aqueous solution. Why? So we are always saying that if we have Fe3+, right, Fe3+ in solution, it also produces acidic solution. Now, why does it produce the acidic solution? We mentioned this when we're talking about the Lewis acid. So we can refer to that. We're talking about the Lewis acid. We explained this. We can refer to that. Good. Now, salt of strong acids and strong bases. Salt made up from strong acids and strong bases are neutral aqueous salts. They are neutral. Right? Good. An example is potassium nitrate. Now, the potassium here is from KOH. KOH. The nitrate here is from HNO3. Now, this is strong, this is strong. None of these ions, the K plus and the HNO3 minus ions, will hydrolyze in solution. So they will produce a neutral solution. If you have salts formed from strong bases and weak acid, then the salts will be basic. The salts will be basic. Now, why are they basic? So we are saying that salts made from strong bases and weak acids hydrolyze to form basic solution, right? So once the base is a strong one, the solution being formed is a basic solution, right? But then that is not the explanation to the concept. Good. So an example given here is the sodium acetate. You realize that sodium acetate would break down completely in solution and give you sodium ions and acetate ions, right? Good. Now this ion coming here, this is from sodium hydroxide. Because sodium hydroxide is a strong base, this ion is a weak conjugate acid, and then it would not hydrolyze, right? But then because this is coming from acetic acid, CH3COH, it's coming from acetic acid, which is a weak acid. So he has made this one a strong conjugate base, right? So this one will interact with water. So then interact with water, just as any normal base will accept a proton from water. Once accept a proton from water, it will form acetic acid undissociated, and then it will give or leave the solution with excess OH minus ions. That will make the solution basic. That will make the solution basic. We make the solution basic. Very simple. So that's what we are saying, right? That the ion coming from the weak acid in play would become a strong conjugate base. And then because it's a strong conjugate base, it can interact with water, accept a proton from water, and then leave us with excess OH minus ions, making the solution basic, right? Good. Now, if we turn the instance and make it a weak base against a strong acid, weak base against a strong acid, yes, so then we will form acidic aqueous solution. The acid is a strong one, so it's not surprising we are forming acidic solution, but that is not the explanation, right? The example we are citing here is ammonium chloride. The ammonium part here, the ammonium part is from ammonia. The chloride part is from hydrochloric acid, right? Now, this is a strong acid, so the ion here is very weak, a weak base, and it will not undergo hydrolysis. The ammonia is a weak base, right? So the ammonium ion here is a strong conjugate acid, right? Now, once the strong conjugate acid, it will interact with water, and just as any acid will do, will give the water H plus ions, right? So it form the hydrozonium ion. Now, because it leaves us with excess H3O plus ions, that's why we are saying that the resulting salt here, or the resulting solution, is acidic. Very simple. Good. So then generally, we are saying that, okay, so this is the last instance, before I go to my generalization. Last instance is when we have weak acid against weak base. Now, for weak acid against weak base, the solution can actually be neutral, acidic, or basic, depending on the K and the Kb's of the acid and bases we are talking about. Should it happen that the Kb is greater than the Ka, right, then the solution is basic. If it happens that the Kb is less than the Ka, the solution is acidic. Then if it happens that the Kb of the base is equal to the Ka of the acid, the solution is neutral. Very simple. Good. Good. So we have given an example here. Now, HClO, Ne3. Both of these are weak compounds. So this is a weak base and this is a weak acid. Now, when they combine, we can only tell whether the solution or the salt is acidic, basic, or neutral, depending on the K of the acid and the Kb of the base. If we compare these two numbers, you realize that the Kb is bigger. Because the Kb is bigger, the resulting salt formed is what? S basic salt. It's a basic salt. We can do it for this instance to HF, which is the acid, and then the trimethylamine, right? And the trimethylamine. Now we compare the salt form. When we compare these to realize that this is a bigger number, the HF is a bigger number, right? So then the resulting salt form is what? Is acidic. It's acidic. Very simple. Good. So this is a table giving us a summary of whatever we have discussed with regards to the hydrolysis of acid and bases. And these are questions. So the first question, we have to predict whether this is acidic or basic or neutral. Now, this one dissociate gives me to give me Na plus OCl minus, right? Now, the Na plus is from NaOH, it will not undergo hydrolysis. This one is from a weak acid, HClO. HClO is a weak acid, right? Because a weak acid, this one will be a strong conjugate base. Now, a strong conjugate base will interact with water and accept a proton. So we accept a proton from water and then leave me excess OH minus ions. Therefore, the solution for the first one will be basic. The second one is KCl. KCl will give me K plus ion plus Cl minus ion. Now the K plus is from KOH. It's a strong base. The HCl is from, the Cl minus is from HCl, which is a strong acid. None of these ions will undergo hydrolysis appreciably, and so the solution here is neutral. Then we have the NH4NO3. Now the NH4 here is from ammonia, right? Ammonia, which is a weak base. The NH3 here is from HNO3, which is a strong acid, right? It's a strong acid. Now the one from the strong acid will not undergo hydrolysis, so the NO3 is out. Now if you come here, because this is from a weak base, it is a strong conjugate acid. And so the ammonium ion here, let me just dissociate it. The ammonium nitrate will dissociate and give me ammonium ion plus the nitrate ion. Good. Ammonium ion plus the nitrate ion. Then this will not undergo hydrolysis. This will undergo hydrolysis. So it will interact with water. And just as any other acid will do, it will give the water H plus. So I'll form my normal ammonia plus H3O plus. Now because of the excess H3O plus given, I would form an acidic solution. Acidic solution. Very simple. Very simple. Good. So many other examples. When a salt which contains both weak acid and weak base ion, then they are saying we should predict whether it's acidic, basic, or neutral, and that would depend on the K and the Kb of the acids we are talking about, right? So now, this is the last example we are supposed to do. I'll just give you the answers and then you would try and explain it to yourself, see whether you understand the concept. So then the first one here will be acidic, right? The second one here would be basic. The last one here, because of the F here, would be acidic. Now, this one in other references can be said to be neutral. So you check your reference well. But then according to my reference, it's basic. So you can prove why it's basic. You can just go and find out why it is basic. So we shall end here. But if you have any question, as we've said already, you can just contact any member of the academic board. I wish you all the best in your exams. We shall continue sometime later. Enjoy.